Okay, the last section in chapter 14 is 14.8. It's change of variables using a Jacobian. So for a single variable, we often will use a change of variables, particularly in Cal 2, to make integration easier. Now we can still do this by turning x, y into some combination of u and v, but it's multiplied by some partial derivatives, or the product of some partial derivatives, product and difference. And the way we represent this product is called the Jacobian. So if we're changing x and y into u and v, then it's multiplied by dx du, dy dv minus dy du, dx dv, which looks like the matrix with dx across the top, du down the left, dy across the bottom, and dv across the right, the determinant of that matrix. So if x is a function of u and v, and y is also a function of u and v, the Jacobian of x and y with respect to u and v is dx, the derivative of x with respect to u, times the derivative of y with respect to v, minus derivative of y with respect to u times derivative of x with respect to v. So when we were talking about the polar coordinates briefly in 14.3, this is where that extra r comes from the Jacobian. Just has to do with substitution and how r and theta work relative to x being r cosine theta and y being r sine theta. So let's see how this works and what it's used for. Primarily, this is useful if your shape for x and y is kind of like a diamond or somewhat diagonal. It allows you to change your bounds into something that's, say, a square or a rectangle. So we'll do 1 and 2 in 2 videos. First we'll do 1. Use the change of variable x equals 1/2 u plus v, y equals negative 1/2 u minus v to evaluate the double integral of 60xy dA over the area region R with vertices 0, 1, 1, 2, 2, 1, and 1, 0. Okay, so what does this mean for us? One thing to note, if x is 1/2 u plus v, that means 2x is u plus v. That means negative 2y is u minus v. If I subtract these two, 2x minus 2y equals u. Furthermore, if I take the negative, for example, 2x plus 2y is 2v. So x plus y, that means x minus y, oh sorry, it's 2u. X minus y equals u, and x plus y equals v. How's that helpful? Let's look at the endpoints and compare them. So we have our first vertices, vertex is 0, 1. How does that compare for u and v? U is 0 minus 1, so that'd be negative 1. V is 0 plus 1, 1. Next one, 1, 2. 1 minus 2, negative 1. 1 plus 2, 3. 2, 1. 2 minus 1 is 1. 2 plus 1 is 3. And lastly, 1, 0. 1 minus 0 is 1. 1 plus 0 is 1. So it took this diagonal, so 0, 1, 1, 2, 2, 1, 1, 0 is kind of like a diagonal here, like a rotated square, and it turned it into actually a different shape in terms of u and v. We have negative 1, 1, negative 1, 3, 1, 1, and 1, 3. So it's much easier to find the area of a rectangle than it is to find the area kind of a diamond, but we'll have worse things to find areas of than that. However, despite the fact that it makes our bound situation more clear, it makes our integral situation a little bit harder. Now, it says I need the Jacobians here. So I need all my partial derivatives, dx du, dx dv, dy du, and dy dv. So the derivative of all of these with respect to the others. So the derivative of x with respect to u should be 1/2. Y with respect to u is -1/2. X with respect to v, 1/2. Y with respect to v is also positive 1/2. So what's our Jacobian? It's 1/2, -1/2, 1/2, 1/2. The determinant of this would be 1/4 minus -1/4. So that's 1/4 plus 1/4, which is 1/2. So that means what I have to do is multiply my integral by 1/2 when I make the substitution from x and y to u and v. Okay, so we've got the double integral. The 60 stays the same. X becomes 1/2 times u plus v. The y in the original problem becomes -1/2 u minus v. And then this whole thing has to be multiplied by 1/2 dA. Now in terms of u and v. Okay, we have a half, a -1/2, and a 1/2. So that would be divided by 8. 60 divided by 4 is 15, so this is 15 halves. I'm going to leave the negative in here. U plus v times u minus v. So we have negative, and that's u squared minus v squared. The negative is going to flip this. So this is now v squared minus u squared dA. So let's use our bounds. We're now in terms of v and u, so now we need to use bounds for v and u. Our order doesn't matter. We just need to make sure we have the right bounds. Here it's clear u goes from -1 to 1, v goes from 1 to 3. So we'll do u first. V is going from 1 to 3. U is going from -1 to 1. This is now v squared minus u squared, and our area is now du dv. Integrate with respect to v, or u first. That would be uv squared minus 1/3 u cubed from -1 to 1. Still a dv on the outside. So if we plug in 1, we get v squared minus 1/3. V squared minus 1/3. When we plug in -1, we get minus, looks like -v squared plus 1/3. So that would end up being 2v squared minus 2/3. Still dv. The 2 I can pull out to cancel out here. So this should become 15 times the integral from 1 to 3 of v squared minus 1/3 dv. When I integrate that, I should get 15 times, it should be v cubed over 3 minus 1/3 v, evaluated from 1 to 3. I'm going to pull the 3 out. So this becomes 5, and this is now v cubed minus v, evaluated from 1 to 3. When I plug in 3, 3 cubed is 27, so 27 minus 3, 1, minus 1 minus 1. So 27 minus 3 is 24, so this is 5 times 24, which is 120. So what does that mean? That means this integral 60xy evaluated over the region bounded by the vertices in terms of x and y, we've now converted to u and v, and that area, or that integral over that area, is exactly 120. And we'll do number 2 in the next video, and we won't do 3.